Okay, let's get right into it. We all hear about how AI is changing everything, but what we don't talk about enough is the insane energy bill it's racking up. Today, we're going to pull back the curtain on the hidden reason why.
I mean, that's a wild fact, isn't it? We're talking about a truly staggering amount of power. And if your first thought is, well, it must be doing some kind of impossibly complex math, you might be in for a surprise.
That's right, the real energy hog isn't the work itself. It's the constant, exhausting trip the data has to take just to get to the processor. And this journey is at the very heart of a problem that's been baked into almost every computer for the last 70 years. It's called the von Neumann bottleneck. And the best way to picture it is a massive 12-lane superhighway that suddenly narrows down to a single toll booth. The cars, that's our data, can only squeeze through one at a time, and the processor, our super fast worker, ends up spending most of its time just sitting there, idling, waiting in traffic. So, how did we end up with this massive traffic jam in the first place? Well, to understand that, we have to go way back to the very beginning of modern computing. So way back in 1945, this brilliant physicist, John von Neumann, he laid out a design that would define pretty much all of computing. The core idea was actually super simple and flexible. Keep the brain, the processor, separate from the library, the memory. And a pathway called a data bus connects the two, acting like the only road between them. And for every single tiny task, the computer follows this cycle. But look how many trips it makes down that road. Step 1, it has to drive to memory to fetch an instruction. Step 3, it drives back to memory to get the data it needs. And step 5, it drives back again to drop off the result. It's just so much back and forth. It's like driving to the library for a recipe, driving all the way home, then realizing you forgot the ingredients and have to drive all the way back again.
Now, here's where it gets really crazy. Over the years, our processors have gotten mind-bogglingly fast. A modern CPU can just rip through billions of calculations in a single second. But getting data from memory, that can take the time equivalent of hundreds of those calculations. This huge speed gap has a name. It's called the memory wall.
Now, engineers have known about this problem for decades. And since they couldn't just tear down the whole system and start over, they came up with some incredibly clever patches and workarounds to deal with it. The main solution is something called the memory hierarchy. And the idea is beautiful in its simplicity. It's basically, if the main library is too far away, let's just build a small personal bookshelf right next to our desk for the books we use all the time. In computer terms, that little bookshelf is called a cache. And it's not just one bookshelf. It's a whole system of them. You've got these tiny, lightning-fast registers right inside the CPU itself. Then you've got slightly larger and slower caches, L1, L2, and L3, all before you finally have to make that long, slow trip out to the main memory. The closer you get to the CPU, the faster and smaller the memory is. So the whole name of the game, the entire goal of this setup, is to score what's called a cache hit. That's the magic moment. It's when the processor needs a piece of data and boom, it's right there, waiting in one of those super fast nearby caches. It's a huge win because you get to avoid that slow, energy-wasting trip to main memory. And the reason caches work so well is that computer programs are actually pretty predictable. They tend to follow two simple rules. First, if you just use a piece of data, you're probably going to need it again, like right away. That's called temporal locality. Second, if you just grab data from one spot in memory, you're probably going to need the data from right next to it. Think of reading a book, one page after another. That's spatial locality. For most of computing history, this whole system of caches has worked wonderfully. It's been an absolute lifesaver. But then, along came modern AI. And AI workloads are a completely different beast, and they're pushing this classic design to its absolute breaking point. Here's the perfect analogy. Think of a traditional computer as a deli. It's making all sorts of different custom sandwiches on demand. It's flexible. And AI, on the other hand, well, that's more like a factory that just got an order to make 5,000 identical tuna sandwiches. The task itself is simple and repetitive, but the sheer scale of it is enormous. And that is the core of the problem. The ingredients for that AI model, its billions of parameters or weights, are so massive they can't possibly fit on the processor's little personal bookshelf, the cache. This forces the AI to constantly make that long, slow, energy-hungry commute to main memory for almost every single calculation it does. And this, well, this is the shocking result. Just look at this breakdown. In a typical modern AI workload, the actual math, the thinking, accounts for only 10% of the energy being used.
A mind-blowing 90% is just wasted moving data back and forth, stuck in that perpetual traffic jam. All that power, all that heat, it's not from doing the work, it's from the commute.
So, if the commute is the real problem, what's the solution? Well, a new generation of researchers is rethinking that original blueprint entirely. They're asking, what if we just tear it up? And the new idea is nothing short of revolutionary. For 70 years, we've always brought the data to the processor. Now, researchers are trying to flip that script and bring the processor to the data. I mean, if you can't shorten the commute, why not just eliminate it altogether? Two main strategies are popping up. Near-memory computing is kind of like building thousands of tiny specialized factories, each with its own small warehouse right next door. But the more radical idea is in-memory computing. This approach actually changes the memory cells themselves so they can perform calculations directly, using the flow of electricity to do the math right where the data is stored, zero travel time. So, does this mean it's the end of the line for the computer as we know it? Well, not so fast. That old design, it still has a super important role to play.
I love this quote from Jeffrey Burr over at IBM Research. He says that for all the flexible, unpredictable tasks of everyday computing, our deli making custom sandwiches, that classic von Neumann architecture is still unbeatable. Its flexibility is its absolute superpower. So the future isn't about replacement, it's about specialization. You can think of it like this. The general-purpose processor, our deli chef, handles all the varied custom jobs. But the second a massive repetitive order comes in, it gets sent over to the specialized AI factory. It's all about using the right tool for the right job. And all of this leaves us with a really fascinating question. We are watching a fundamental shift in computing, driven by the unique demands of AI. Is this the first step towards a completely new kind of computer, one that's designed not for flexibility, but for pure, raw, data-centric intelligence? The answer to that question is going to shape the next 70 years of technology.